and that's a slab design. A slab design is a part of actually this reinforced concrete design. But because we have a lot of chapters and we have to cover in one semester, that's a little too much. And we know that in some different other universities, they have a concrete 1 and concrete 2. In concrete 1 for undergrad, both of them are for undergrad, and another advanced reinforced concrete for master. But over here, we have just one reinforced concrete design. And I don't like to cut any part of the reinforced concrete because you should have at least a minimum of knowledge about each section of this reinforced concrete design. And because of that, I added this part to our lecture, slab design. And I'm going to give you actually designed for one-way slab and two-way slab, and we understand here, and we will learn what is the difference between one-way slab and two-way slabs, and how to design them. Based on the old code, actually, there were some tables for two-way slab that is the hardest actually part in our design. And let me answer one of the chat. Is this going to be included in the final? Yes, this is part of the final. And I will give you at the end of this, actually, at the end of the classes, I think it should be next week. I will give you the chapters that I'm going to give you question from those chapters. I'm not giving you all the chapters. Yeah, I will give you a few chapters, and the questions should be from those chapters. And this one is included. Okay, so old generation of ACI had some tables for two-way slabs. And on new versions of ACI, there is no table, and there are different methods. And these methods, they have a lot of restrictions. And sometimes if you have a special structure, you cannot design that based on the code. And in this class, I'm giving you the old method that is actually, you can see tables and how to use those. And fortunately, you will enjoy how to use this stuff. And when I was a student, actually, I did some research on this one, and I used finite element analysis and checked them with the numbers, and they were good. So those are actually good numbers that we can rely on those. Okay, let's start a slab design. What's the slab and what? A slab is horizontal plate that is covering the floors. Yeah, that's the structural horizontal part of the building. Yeah, horizontal element that is covering the floors, like this one, like this one. Sometimes you have just two supports. Look at this, two supports. There is no beam or wall here. You have one wall or one beam, one wall or one beam, and nothing at this side. This slab is working one way. What does it mean? It means that the load, if we consider, for example, just 1 point load, yeah, something like this. Imagine one guy just stand here. So its weight will go just to this direction because there is no support at the other side. Look at this, there is no support. So the weight will go just this direction. At this side, there is no support, the load cannot be transferred. So we'll go to one way. So we call that one way slab. Yeah, one way slab. But In the case that we have fourth sides support, and that guy actually stand here, as you can see, its load will go to this direction plus that direction at the same time. Yeah. So we call this two-way slab. So one way, two way. As you can see, those two, if we consider those strips, yeah, the guy will stand here. Yeah, that's the guy. Wait, will stay here. Then one strip from this side, another strip from other side will transfer its weight to the supports. If there is no beam here or wall or no support, just you have to remove this actually pink strip because there is no support here. So the whole load will go to blue side only. It should be one way. But if we have both sides, the load will be transferred to both sides. But let me make this more clear. Imagine you have a salon, that's a plan view, and you have 4 walls or 4 beams, doesn't matter, that's a plan view. Yeah. So you have a support like this, that's a beam or wall. I will show that with double line. And we have reinforced concrete slab on top. So this side, just imagine this side is 100 feet and this side is just 20 feet. So that guy stands here. Yeah. So we have one strip at this side, another strip going that side. So can we consider this as a two-way slab? Yes, but because the load will be transferred to the easiest side. Remember, when you put a load here, this load is very close to the both sides at one side, very far from the other side. The load will go to the easiest way, not the hardest way. This load must be transferred a lot to reach to the support. But at this side, the load will transfer a little to reach to the support. So in this case, this slab will work closer to one-way slab rather than two-way slab. So how can we make a limit to show if you are at this limit, consider one-way slab, otherwise two-way slab. That's the rule. If the long length, if I call that LB, long length, LB, short length always LA, yeah. So if LB divided by LA is greater than or equal to, consider that one-way slab. So for example, 20 feet, 10 feet, yeah, greater than or equal. You can go with one-way slab. Just load will be transferred in one direction. The percentage of the load that will be transferred to the long side is very small percentage. And because of that, we can neglect that whenever LB over LA is greater than 2. Just remember this, that's a good limit. If it's less than 1, then it will be transferred as a two-way slab. And two-way slab actually load, if you want to transfer this load, imagine this side is about 10 feet, the other side is 8 feet. So it's not double of that side. So it's two-way slab. That's a plan view. In this case, the load that will go to the short side is this triangle, trapezoid to the other side, and triangular to this side. So one triangle will go here, another triangle to that side, trapezoid on this beam, trapezoid on the other beam. So if you have two-way slabs, in your structure, the loading on this beam is not uniform load. If you have a slab, because it's two-way slab, you should consider trapezoid load on this beam, triangular load on the beam perpendicular to other side. So the load is not uniform, just rectangular uniform. It's trapezoid and rectangular for two-way slab. If it's one-way slab, so imagine this side, if you have, instead of this one, you have 10, and let me plot another one. If you have 20 this side, yeah, and you have, for example, 8 here, as you can see, it's more than 2. So it will act like a one way. In this case, because the load will go just this side, so half of this load will go this direction, half of that load will go this side, and it should be uniform rectangular load on this beam, uniform rectangular on that beam, 0, on this beam, 0. That's the difference between two-way slab and one-way slab for the loading. So hopefully it's clear. If it's not clear, please ask question. I will try to give you answer to your question to make that completely clear. So remember, one-way slab load will be transferred to one direction. Two-way slabs to two directions, two perpendicular directions. Yeah, something like this, as you can see. If the limit of longer length span to the shorter span is greater than or equal to, you can consider that as a one-way slab. Even if you have 4 walls or you have 4 beams at 4 sides, still you can consider that one-way slab, because the percentage of the load that will be transferred to the long side is small. Short side will transfer the maximum load. Yeah, so that's it. So that's the difference between one-way slab and two-way slabs. Like always, if you have question, raise your hand or stop asking your question. I will stop and I will back to the slide that you have questions. Okay, so let's go with this system. Imagine you have a system like this. You have beam here, beam there, and there is no beam this side. So in this case, there is no support. So it will act one-way slab. Look at this, one-way slab. So half of the load will go this side, half of the load will go to other side. Easy. If you have 4 side supports, in this case, you have 4 beams. So in this case, you call that two-way slab. If the long span divided by short span is less than 2, we call that two-way slab. If it's more than 2, one-way slab. How can we transfer the load? With 45 degree. Those triangular at both sides, at 4 sides, are 45 degrees. 45 degree, 45 degree. They can actually meet each other. 45, 45. Then connect these two. So you will get trapezoid load on this beam, trapezoid on the other side, triangle, triangle on this one. So we call that two-way slabs. Okay. Imagine we have a two-way slab like this. As you can see, beam, 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 beam. And then because of some reason, you add another beam at the center of these two. Look at this. At the center, you add another. So your slab is not this anymore because you have support, 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 support. Between 4 supports, you have a slab. This slab, in this case, is less than, actually greater than 2. This span is greater than 2 times of that one. So you create one-way slab. The loading here, 1/2 will go to this, 1/2 will go to other one. For this side, 1/2 of this means 1/4 of total will go to this, 1/2 or 1/4 will go to this side. So this beam will actually tolerate 50% of the load, because 1/4 to this side, 1/4 to here, 1/4 to that side, 1/4 to this. So half of the load will go to this beam. So in this case, your slab will work one-way slab. If you add a beam here, Just remember. If you add another beam other side, so you will get two-way slabs, 4 two-way slabs. Yeah, if you have a structure, the architect asks you, I want these beams to be exposed. I like to see that from the bottom, and I want from both sides. So in this case, you have to check for two-way slabs, because you have one support, 1, 2, 3, 4, and the small span ratio of the long span to small is less than 2, so you have 4 two-way slabs. Just remember, you can check what kind of slab do you have, and then today we will learn how to design one-way or two-way slabs. Sometimes the slabs doesn't have any beams. It has just column. So as you can see, you have a slab and then column, column. That's it. We call that flat slab or flat plate. This one is not, you cannot design this based on this methods. Yeah, because that's another system. The shear here is very critical along this. It can be punched. So this kind of a slab is limited for 2 or 3 stories at the most. You cannot go with more than that. So there are some limits for this. The spans are limited. Then you have to create some stuff around this column to tolerate the shear. I'm going to show you some other pictures to make that more clear. As I told you, you can see there is no beams here, but because we have huge shears here, then we have to add something underneath to get a bigger thickness of the concrete and can tolerate shear. So that's the flattest slab. If the load is too much, then we have to add this top columns or cap on the top of the columns to give us more shear strength for the slabs. Another slab is waffle slab. So you can see a lot of, this is one, we call that joist. So these are joist. Look at this. These are joist. So joist, 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 joist. So we have a lot of joists everywhere. If there is no beams here, look at this. There is no beam. So this one should be calculated like a flat slab, because there is no support. You can see there is no support here. And over here, those are voids. As you can see, there is a hole here. There is some voids here, so it can reduce the weight. But because you have thicker kind of elements for tolerating the shear and bending, so you can transfer more load than just with the small thickness of uniform thickness. Here is kind of flat slab, but can tolerate more load. If you add beams here, so consider you have this waffle slab and you have beams here. In this case, it might be double one-way slab or two-way slab. If the longer span divided by shorter span is greater than 2, one-way slab. If it's less than 2, this waffle slab will act like a two-way slab. So these are important. If you go to work and somebody gave you this slab and asked you to design this, you can't find anything in the book for this kind of design waffle slabs. Just, two-way slab or one-way slab, that's good enough. Find the moments, and then instead of that slab, you have to design this beam. That's it. Yeah, the moment will be transferred by these joists. Yeah, joist at this direction, joist at that direction for two-way slab. Negative moment, positive moment, negative moment, negative, positive, negative for both directions. How? We will learn today. Okay, so these are the information for a start of this system. And minimum ratio of the rebar that we have to install in the slabs are for shrinkage, and there is no other parts that you have to check. Just these are the minimum. So slabs were grade 40 and 50 means FY 40 or FY 50. You have to add 0.002%. Rho is equal AS divided by BD. We will check on this actually example here. We will learn how to use this one. If you are using grade 60, means FY 60, 0.0018. If you use something more than 60, that's the equation. But we are not using this. We are between these two. Most of the time, 99% of the time, we are here. Just remember, this is good reference for you to find the minimum percentage. Okay, how to guess the thickness? These are just for helping us to get the thickness. It's not something that you have to use it. No, it's just something that you can start with this if you have no idea, or you can change it if you want. If you have simply supported beam, you have one span, simply supported. The thickness should be L over 20. Yeah, for one-way slab. Remember, these are for one-way slab. So simply support span divided by 20. If you have one end continuous, look at this, simply support, but the other side is continuous. So means for this span, you can go L divided by 24. For the other side, no, because you have cantilever. It's not actually one-way continuous. This side is continuous as well. This side is, so you have both end continuous like that side as well. So in this case, you are in this category. Yeah, both ends continuous. So in this case, L over 28. If you have cantilever, so I put these lines to actually I put these lines to help how to read this actually chart or picture. For both ends continuous, this one, and like this one, continuous at both sides, continuous at both sides. So you are in this. One end continuous means this span L over 24. This span both end continuous. You have cantilever, you have continuous, both end continuous. That side for cantilever. Okay. Another stuff that we want to learn is percentage of the rebar that I mentioned on the last slide. How can we calculate that? Go with the spacing. Yeah. Imagine we have number whatever rebar at S spacing. So consider your B equal S. Okay. Your percentage is AS divided by B times D. That's not good sign actually, like X. No, it is times. So AS divided by B times D. Okay, what's the D? D is the total thickness, T, minus 1 inch cover. Most of the time is 1 inch cover. So from center of the rebar to this bottom, at least 1 inch. Yeah. So T minus 1, if it's 1, is your D. B is your S, spacing between your rebar. That's it. So you can find AS divided by BD is your rho. This rho must be greater than or equal this percentage. That's it. So how to calculate that rho? This is the way how to calculate this one. Example, calculation of the rebar in a T equal 5 inch slab for number 4 at 4.5 inch center to center. Okay. What can we do? This is your S, number 4 at 4.5 inch. This is your S, spacing between the rebar. So B is equal S. That's it. Your D is equal T minus 1 inch. We assume that 1 inch. Okay. So, and then rho is equal. Your AS number 4 is 0.2 square inches. So your AS 0.2 divided by S means B times D. That's your percentage. And this one must be greater than these two numbers. as you can see, is bigger than even for Fi or that one, 0.002, and you have 0.011. So that's a good actually percentage. Maximum percentage reinforcement in slab would be less than rho with epsilon 0.05. You can remember for the beam design. Yeah, rho balance, we rho 004, rho 005. How to calculate it? You can calculate that. Instead of rho s, you should consider 0.005 in that equation. That's your maximum rho. Okay. Yes, Safa, what's the question?
Do we always assume 1-inch cover?
Look at this. Yes, you should look at it that you have to assume, then check based on the rebar size that you have. Clear cover must be 3/4. Yeah, this is the code that we went through that before, but here we need that. I put that here. Clear cover 3/4. And from center to the bottom must be at least 1 inch, whichever is greater. Yes.
Is D from the top of the slab to the rebar or to the bottom of the slab?
No, to the center. From center, that's to the center. Yeah, that's this distance is here. D is from the rest of that. Look at this. This is your D, and this distance, I put this line here from center. Yeah, from center at least 1 inch, whichever is greater. So this distance must be at least 1 inch. And at the same time, you should have 3/4 of an inch clear cover. So in this case, we have number 4. Yeah, number 4, the diameter is 4 divided by 8. It means half an inch. So diameter is about half an inch. So for half an inch from center to here is 1/4 of an inch. 1/4 of an inch plus 3/4 means 1 inch. So D is perfect for number 4. If you go with number 5, 1 inch is not that acceptable because 5/8 plus 3/4, you need more than 1 inch. So at least you need 1 inch. Then go with half of the diameter plus 3/4. If it's less than or equal 1 inch, you are good. If it's more than 1 inch, go with that number. Then consider that minus T minus that number must be considered for your D. Is that completely clear?
It is clear, but can you just repeat it slower one more time so I write it down, please?
Let me, yeah, look at this. Over here, I will go with this example, number 4. Number 4 diameter is 4 divided by 8. Yeah, 4 divided by 8 is diameter for this. So from center to here is radius of this bar. Radius of this bar is diameter divided by 2. 4 divided by 8 is half an inch, your D diameter of this bar. Divided by 2 means 1/4, 0.025. Yeah, 1/4. 1/4 from center to the bottom of this rebar. Then we need at least 3/4 of an inch of the clear cover, means from the bottom of the rebar to the concrete, at least 3/4. 3/4 plus 1/4, that was radius of this rebar, you will get 1 inch. So the minimum from center to the bottom must be at least 1 inch as well. So we are good. Number 4 is exactly per code. Yeah. If you have number 3, okay, 3 divided by 8 divided by 2 means 3/16. 3/16 is your radius, is less than 1/4. Less than 1/4 plus 3/4 is less than 1 inch. So if you use number 3, distance from center to the bottom is less than 1 inch. So in this case, you should go with 1 inch. Never less than 1 inch. Yeah, that's it. If you use number 6 divided by 8 means 6/8 diameter, divided by 2, 6/16 is more than 1/4. That one plus 3/4 is more than 1 inch. So in this case, you should go T minus 3/4 plus 6 divided by 16. That's the radius of that number 6. and it's more than 1 inch. Is that clear now?
Very clear. Thank you.
Okay, very good. Yes, yes, Chris, what's the question?
So just to clarify, if it was greater than 1 inch, we could still use that rebar?
If it's greater than 1 inch, then yeah, you can use it. But for D is not T minus 1. T minus 1 if the diameter radius of the rebar plus 3/4 is less than equal 1 inch. Then you can go with 1. But if it's more than 1, just go D is equal T minus that bigger number, means radius plus 3/4. Is that clear now?
Yes, sir.
No.
Thank you.
And then if your rebar
Sorry.
is smaller, where you end up with less than 1 inch, you have to increase the clear covering space.
Clear cover, yes, you will get more than 3/4. Yes, and you should go with D equal. You don't need to go with more than 3/4. You can still go with the 3/4, but for the D, you should consider that 1 inch. It means that they have to put a little bit bigger dobies, yeah, to send that to 1 inches. Yes, actually, it should be a little bit greater than 3/4 when diameter is less than 4 divided by 8, means half an inch. Did I give you the answer?
Yeah.
Okay. Okay, so based on this stuff, these are our knowledge that we should have, and it has nothing to do with the design of the slab so far, yeah? But these are important because those are the code that we have to follow to make sure that the final design is based on the code. Okay, then we have some actually tables that just these are good for your information, yeah? If you have a one-way slab, and you want to design that based on the these numbers instead of just finding the negative moment, positive moment by yourself. So these are the factors for negative moment at this side, means tension on top, negative moment. Positive moment, tension at the bottom. These are the factors. Negative moment here, negative moment, positive moment, negative moment. So for each one, factor times omega u, uniform load that you have, times L square. What's the L? From face to face. So you know the loading on this slab times factor omega u, means 1.2 dead load plus 1.6 live load. That's your omega u. L square, whatever is 10 feet a square, times omega u, times this factor will give you negative moment, times this factor, positive moment, times this factor, negative moment for this strand, then go to other strands. Okay, so why we have so many factors we will learn. If the support at this side is unrestrained, what does it mean, unrestrained? If you have a slab sitting on the beam with no connections, it will sit with no rebar going from this to that one, and they didn't pour them together. If they pour them together with no rebar, still you should consider that unrestrained. Yeah. So when there is no rebar connect these two together, so you can call that unrestrained. Then in this case, use these factors. It means that at this case, look at it, this is simply support. So you will not get any negative moment. So over here, you will get 0 factor times omega UL square, means no negative moment for this case. Positive moment, 1/11 times omega UL square, positive moment here. What about the rest? Because the rest is can be continuous, even if it's not sitting inside, is not rebar connected the beams to the slab. Doesn't matter on that case because it's continuous here. So you will get negative moment. Just start and end. If you have unrestrained, you will not get any moment negative. But for continuous, even if the beam is not connected to the slab with rebar, still you will get negative moment. So whenever you can't see any factor here, it means that these factors are good for the top one and for the bottom one. They didn't rewrite them to make that too many numbers. Let me answer one chat. So depending on the moment, we put a positive or negative for the factor. Yes, or you can see, because at this side, this is negative moment, always at support. Negative support, positive midspan. Negative support, positive midspan, negative support. If you want to show that with negative, it's up to you. Just put negative. It's better because you are not going to be confused yourself to consider rebar on the top or at the bottom. Negative moment, rebar on top. Positive moment, rebar at the bottom. Negative moment on top. It's good idea to consider a negative on top. Yes. Okay. So these are the factors. If you have a spandrel, what's the spandrel? If the beam and the slab are connected to each other with rebar. Yeah. So in this case, they will act like a fixed object. So in this case, use these as your factors. Factor, you can see negative moment. Yes, because it's fixed connection, you will get negative moment. So negative moment, positive, negative, and the rest. If you have column, a slab is supporting but by column, negative, positive, negative, negative, positive. Just we have all those factors, but because they are the same, they didn't wrote them. So these factors are for the top and bottom. That's it. Yeah. And beams with more than 2 spans. If you have with 2 spans, go with these factors. Unrestrained, like this, go with that. Yeah. Other side, look at this 0, 1 over 11, because start and end is unrestrained. So no negative moment here for this case, no negative moment here at that case. But negative moment at midspan, because it's continuous, it can support negative moment at midspan. So you can see unrestrained, spandrel, columns. That's it for 2 span. Slabs with spans less than 10 feet. If you have a slabs with 10 feet and less, negative moment factor. So you cannot use this for a spandrel. This one is good just when the slab and beam are poured with the rebar, connect those together. So that's factor, negative, positive, negative, negative, positive, negative, negative. Use the same equation. Yeah. And if the sum of the column stiffness is greater than 8 times of sum of the beam stiffness, that's hard to use. Yeah, if it's better to do it by hand. It's easier than this to go and find the stiffness of the column and find the stiffness of the beam time. No, this is just for your information, but you don't need to actually worry about this. Doing by hand is easier. And as you can see, these numbers is almost the same. Yeah? Okay, so these are some examples, some charts that ACI provided, and this is an example how to design that slab. Okay, let's see what can we do. Imagine we want to design a 2 spans slab. That's one-way slab. It will transfer just load at one direction. And with this information, clear spans are 15 feet. Okay, those are 15 feet. Live load that we are going to transfer 100 pounds per square feet. Yeah, that's for the dead load. It should be just the weight of this concrete. Imagine this is a parking lot. So concrete is exposed, so they are not adding anything to that one. So dead load is just weight of the concrete, and live load is 100 pounds per square feet. We know F prime C and Fy for KSI, 60 KSI. And we are going to use the factors based on ACI. And we know that they put them together, and you as a designer, you know what you want. Yeah, you know that. So we know if it's spandrel or it's unrestrained. In this case, spandrel. They're put together with rebar, connect them together. Okay, we have to find the minimum thickness. Okay, minimum thickness, as you can see, it's when it's a fixed connection or a spandrel, looks like it's both sides continuous. Yeah, because it's a fixed, looks like it's continuous and it can tolerate moment at this support. As you can see here on this first one, if you both ends continuous like this side, you can go with L over 28. Yeah, L over 28 for both end continuous, because we have fixed or spandrel at start and end. You can consider this as a continuous because you will get negative moment. Okay, so we will go with L divided by 28, 15 times 12 divided by 28. This is a guess. 6.45. We will go with 6.5 inch thickness. So the slab thickness is 6.5. Okay, because it's reinforced concrete. If it was concrete, only was 145 pound per cubic feet. But with rebar, we will go with 150. Yeah, that's the unit weight of reinforced concrete times thickness. Yeah, because it's inches divided by 12 feet. So you will get 81 pound per square feet, pound per cubic feet times feet, pound per square feet. Yeah, that's the dead load. Okay, dead load times 1.2, the live load times 1.6. This is your omega U. Yeah, and most of it will go with 1 foot of the slab. Yeah, so let me show this. That's the easiest way. Whenever you have a slab, so consider this is our slab. Yeah, that's a slab. So in order to design this, we will go with 1 foot of this. Yeah, this is 1 foot. 1 foot. Okay, so this is pound per square feet, means everywhere times 1 foot, you will get pound per foot. That's uniform load on 1 foot of your beam. Yeah, one-way slab is 1 beam. So that's it. If you know how to design the beam, you know how to design one-way slab, and also how to design two-way slab. We will learn. Okay, that's uniform load on 1 foot of the beam. So this number times 1. So this load is uniform 257 pounds per foot for a slab that the width is 1 foot. That's it. Thickness 6.5. Okay. How to calculate the moment? We are going to use the table. As you can see, I put this here for 2 spans. Okay, for 2 spans, and we are in spandrel. Look at this. This is ours, and because it's 2 spans, both of them are should be the same. Yeah, it's for more spans. If you go, it's for 2 spans, you will get negative, negative, the same factor, positive, positive, same factor, negative, negative, the same factors. Yeah. So how to design that? Find the moment for M negative. That factor times uniform load times L square. Okay. What about this negative? This one, this factor. Look at this. This is for the first one. 1/9 for negative moment. 1/9 times uniform load 0.02, 0.257 kips divided by 1,000 kip per foot, not a square foot, because we went for 1 foot. Yeah, and because of that, don't forget to check this always. Yeah, times L square, foot square, times pound per foot, you will get foot kip. Yeah, if it was PSF, you will get kip, and that's wrong because moment cannot be kip. Kip is good for force, not for moment. Moment should be foot times kip. Okay, so this is the negative moment. Do the same for this one. This factor 1/14 positive moment times uniform load KSI span in the power 2. That's it. Do for negative. That's it. You have the moments, find the AS. How can we do that? We know thickness of the concrete, we know D, yeah? So we know B, 1 foot. We know D, assume that T is equal, we assume that we have 1 inch from center to the bottom. We assume this, then we have to check it, okay? So D, 5.5, we assume at the start. F prime C, F5. What's the best equation when we have everything? We have moment, we have the size. In order to find AS, you can remember I gave you that equation, long equation. That's the long equation, yeah? Plug in these numbers here. Just try to use all those information with the same unit. So PSI, foot kip should be inch pound. So times 12 times 1,000. Yeah, this number times 12 times 1,000. As you can see, that number times 12 times 1,000 inch pound. For negative moment, you should use positive. Doesn't matter, always positive. But I put negative here. This is for negative moment, 6.4. I will use that in this equation. Must be positive, even if it's for negative. Yeah, negative is the sign that we show that. But in the equation, positive. Yes, what's the question?
This might be a stupid question, but how do you know that it's negative moment at interior and then positive at midspan?
So look at this. Whenever you have a beam, always in regular loading, yeah, you will get a moment diagram should be something like this. I show that badly. Yeah, something like that. It should be a good line here. It's not like that. Yeah. So this is not the same direction as this one. When you have tension at the bottom, we call that positive. When you have tension on top, you call that negative moment. That's it. So the beam will deflect it like this. Look at this. So in this case, when you push this side, you will get crack here. When you push it down, you will get crack at the bottom. When you push this down, you will get crack on top. So negative moment, positive moment, negative moment.
Okay.
Did I give you the answer?
Yes, you did. And what's the 150 in the weight for the solution? You said it's 150 times 6.5.
Oh, look at this. That's the uniform load. That's the unit weight of the reinforced concrete. If it was concrete only, if you can remember from the first class that we had, I gave you the unit weight of the concrete by itself, no rebar. It was 145 pounds per cubic feet. Because it's reinforced concrete, so it should be a little actually heavier. So we will consider 150. That's the unit weight of the reinforced concrete times thickness will give us pound per square feet. That's the uniform weight of this beam, a slab, everywhere on this slab. Then times 1 foot, we change that to pound per foot. And we are using that here, divided by 1,000, kip per foot, because we check for 1 foot width of that slab. Is that clear?
Yeah, so we always should use 150, right?
Yes, yes. Then in future, you as a designer, imagine you are designing a reinforced concrete slab that you have huge load on top. So the percentage of the rebar is high. So in that case, you can change 150 to bigger number. Do you know what I mean? These numbers are just some guesses for the start. But if you have 4.5% rebar in your slab, so it should be heavier than if you have 1% rebar. So how can you show that? With changing this. Yeah, that's the best way. But for this class, 150 is good. Or if I want, I will give you what unit weight you should consider for reinforced concrete. Is that good enough?
Yes, thank you.
Okay,
Professor, I have a question.
sure.
At the interior support and the midspan and exterior support, when you calculate the moment, the unit doesn't make sense to me. Let's just say that 0.257 is going to be PSF, and then 15 squares.
No. Look at this. This is not PSF anymore because I times 1 foot. Yeah, because I mentioned that this is uniform load everywhere. Look at this. This is your slab. Yeah, I will try to show 3-dimensional. Just imagine this is 3-dimension for this slab. This is a slab. So this unit weight 257 means everywhere, pound per square feet, means on the whole area. You have 257 pound per any square feet, means 1 foot by 1 foot there, 1 foot by 1 foot, you have 257 pounds. Another 1 foot by 1 foot, you have 275. Another 1 foot by 1 foot, you have 257. That's pound per square feet. But because I want to design this and make this easier, I will go with 1 foot of this. So for 1 foot, look at this, 1 foot by 1 foot, you have 257. 1 foot by 1 foot, you have 207. So you have 257 per foot because I consider that 1 foot in our calculation. So this one times 1 foot, you will get 257 pounds per foot. I hope with this diagram it's clear because 1 by 1, one of those lengths is 1 foot will go to the length, another times 1. So the unit for this will be changed to pound per foot just on linear, not on the surface. It's linear pound per foot. And this is pound per foot times foot square. You will get foot cubes.
Got it, sir.
Can I give you the answer?
Thank you.
Okay.
I had a quick question, Professor.
Yes.
I actually have 2 questions. So the trial thickness of 6.50 was just calculated from the table 12.1, right? Is it just rounded up to 6.50? Was that?
That's correct. We calculated 6.43. So it's better to round it. Even if you want, you can go with 7 inches. But because adding to it will give you uniform load for the whole structure, it's not that good to go a lot more than this. You know what I mean? And because of that, 6.43, 6.5. We're not going to 7 or something. Yeah. Try to keep it as close as you can to this one.
Okay. And then also when we're choosing the factors, so are we always choosing that middle row factor when we're doing the support?
No. Look at this. This middle row is for a spandrel. Whenever the slab and beam are connected, and because of the pick this. Good question. If it was unrestrained at the start and end, we should go with this one. Plus these 2 should be on top as well. If it was column connection, then we should go with this plus these 2 at the bottom as well. Okay. What's the other question? That's it?
Yeah, sorry, that was it. Thank you.
Okay, very good. So right now we calculated all the moments. Yes, what's the question? Question. If you're talking, I can't hear you. Just make sure you're not on mute. Chris.
Sorry, I just had that from before.
So mu. So we calculated negative moment. I put this negative here just to make that clear. But always using the positive amount of that. Yeah, just a negative. But the rebar should be on top. This negative, just the meaning of this negative means this. You shouldn't use negative on this for mu. Hopefully you can remember this long equation. Yeah. So plug in all the numbers. What's the B? 12 inches. D, we consider T minus 1, 5.5. Prime C, Fy, moments or feet cubes must be pound and inch. So times 12, times 1,000, convert to it. And we assume that your fee is 0.9, yeah, for a slab, 0.9 fee. Then go to this equation and find AS negative 0.029. AS positive doesn't mean that you will get negative number here. No, you will get positive number always. Yeah. And for 1 plus and minus, as you might remember, I told you that you should go with the negative number. Yeah. For the A, always with negative signs. Just refresh your memory for the beams. Then you can calculate. Please, after this class, go and with those numbers and these numbers, try to find this AS. Please do it tonight, not tomorrow, tonight. You can calculate the same numbers. If you can't, something is wrong. Yeah. Just use this equation with this information. Then what's the AS minimum? Because we are using Fy equals 60. So your minimum is 0.0018 based on the table that I showed you, times B times T. What's your B? B is 12 inches. What's your T? 6.5 inches. Yeah, that's T. That's the AS mean, 0.14 square inch. You can see you use 0.29, 0.17, 0.1. So this one, this negative, we should use a little more because it's less than rho mean. Look at it, that's the minimum required. You need 0.14 per foot because you consider B equal 12 inches. And these are per foot of the slab. So this is good, more than minimum. This is good, more than minimum. This is not good, less than minimum. So we have to use at least 0.14. That's it. How can we find the shear? Let me show another things right now here. In order to find the shear, that's the shear. Shear in end members at the first interior support means here. First interior support. This is the first interior. First exterior, first interior, second interior, go to that side. First interior means here, you will get the maximum shear, 115 times omega u L divided by 2. That's it. That's the equation. Okay. How can we find the shear factor? Means 1.15. Omega u L divided by 2. That's it. Yeah, that's the same equation that we saw over there. Factor means 1.15 times omega u, 257 pounds per foot, linear foot, times L, 15, divided by 2. Yeah. And because we should go with D from face of the support minus D is 5.5. D from face of the support, D divided by 12 times uniform load. Always like this. So 1.15 omega u L divided by 2 minus omega u times D divided by 12, convert to feet. That's your V that you should check. Then most of the time, slab has huge capacity in shear and we have no problem, but we have to check it. So in this case, we will check just the nominal concrete by itself shear strength. As you might remember, VN, VC concrete only with no shear reinforcement. 2 lambda square root F prime C BD. Lambda normal concrete 1. F prime C 4,000, not 4 KSI, 4,000. B12, D 0.5. That's it. As you can see, this one is 4 times as big as the other one. So no shear reinforcement is needed. As I mentioned, slabs are very strong in shear, but we have to check it. That's it. Okay, that's it. As you can see, this is the design of one-way slab. As you can see, just you have to read this, find the moment, then the rest is like a beam. That's it. You don't need to actually do anything extra. Just continue based on the beam for the rest. Okay. Two-way
Professor,
slab.
can you go over the
Yes.
ultimate shear again?
What ratio? Which part? Please
The
let me know.
ultimate shear, yes.
Ultimate shear. Look at this. Ultimate shear. You can over here is the factor is 1.15 times omega u ln divided by 2. Okay. I wrote that equation here again. Factor omega u L divided by 2. Factor was 1.15 times omega u 257, that uniform load. A span 15 feet divided by 2. Minus D from face of the support, yeah? Shear D from face of the support means omega u times D divided by 2. That's always your equation. Yeah, that's the shear from D from face of the support. That's the maximum shear. Then find this Vn. The only thing that we need to actually, I don't need, I have to check times phi, because this is Vu, this is Vn times phi for shear. But because it is too bigger than that, for sure, if times 0.85 or 80 cannot change anything. And because of that, we didn't dig more through this. Yeah, just remember, this is Vu and this is Vn. Vn times phi for the shear. We must be comfortable with that. But because it's too big, there is no actually concern for that case. Is that clear for everybody?
I'm still very unclear on the second term of the VU. I get the first term is the shear in the members of the first interior support, but the 257 multiplied with 5.5 divided by 12.
Look at this, that's for the beam. As you might remember, whenever you have a beam, you can remember from that shear. The critical section for the beam is not at support, is D from face of the support. This D from face of the support. So if you have a shear diagram like this one, so you don't need to calculate this as your VU. Go D from face of the support. You can remember we work on this one with the shear diagram and we calculate it here. D from face of the support. What's the D? Concrete to the center of the rebar. Yeah, that's your D. D is this D. This is D. D from face of the support. Read this number. How can I read this number? When you have this load here, this load is your omega u, is 257 per kip per foot. Yeah, that's your uniform load. Okay. So that's your uniform load. D from face of the support, I want to find this. This load should be VU minus, because we will go this way, minus omega u times D. That's it. VU minus omega u times D times this length. Omega u times D, that's the equation. Clear?
I'll have to take a look. Thank you.
Yeah, just remember this diagram and you have to work on this, because for sure you need this a lot, not just for beam, for a slab, for any case. D from face of the support will give us the maximum shear that you, the element must be carried. Yeah, so you now you calculated VU, that's your VU, but this is the bigger than this. You should go and find D from face of the support. That is a smaller than that. Means omega u, because you have omega u everywhere, times this length will be reduced from that one. You have a support. Yeah, look at this. You have a reaction. That's your VU. Yeah. Shear diagram for this beam is this one. Okay. And you want to find D from face of the support. Okay. And you have uniform load 257. So 257 times this length will be reduced from RU. If you might remember, I wrote that based on RU and omega u. So always you have this case. Your RU minus omega u times d. That's it. Any other question? Okay, so we are almost done with one-way slab, and for two-way slab, you need to learn how to read these tables. That's it. That's it. You don't need to do anything else. Just read this table. For positive moments meet at the midspan. Yeah, at midspan. So these are different cases. What does it mean, these cases? When there is no lines at the sides, you can see there is no hatch around this, nothing. It means that this is simply supported. Simply supported. This means that there is no rebar connection between beam and slab. That's it. Simply supported. When you see these hatch lines, it means that the rebar is included. So fixed supports all around. Fixed supports at the short sides and simply support other side. Fourth sides we have supports. Yeah, these are not one-way slab. We have 4 side supports, but some of them or all of them are fixed. Some of them or all of them are just not fixed, simply supported. This is fixed support everywhere. This is case 2. Case 3, a small span. If you have 20 by 10, 10 side is fixed, 20 sides is not fixed. This is the other side of this. If you have 20 by 10, but 20 is fixed, 10 is simply support. As you can see, these are the same but different fixed. So it can cover every cases. If you have simply fix. Fix one side, 3 sides simply. Fix one side, 3 other sides simply. Yeah, just longer span, shorter span. So you can see which side you should use. So LA, small span, LB, larger span, always. M, the factor that is here. If a small span is equal, long span means 1. You have a square slab. So these are the factors for M positive, but for dead load only. So M positive coefficient for dead load. That's the equation. For CA dead load, all those that you can't read are the same. Because of that, I just wrote those clear. The rest are the same. CADL, CBDL, CADL, CBDL. All of them are the same. This is the factor. This CA, yeah, CA for dead load. As you can see over here, sorry about that. Everything CADL, CBDL, CADL. Yeah, I mentioned that. Sorry about that. Let me answer chat. I'm sorry, but I still don't understand why we subtract this from the shear in the one-way slab. Okay, let's go and back to other one. Look at this. One more time. Let me go through this one. Imagine we have a simple supported beam. Yeah. It has 2 supports. You have that's from the beam. It means that, look at this, less than for 12 weeks, we can forget about all this stuff. And it's completely normal. And we cannot, even right now, you think you got it completely. Next 2 weeks, if you are not reviewing this every day, you will lose it. Yeah. But I hope the concept will stay with you. But in future, if you have a concrete design in your real job, you have to go and review this stuff to make sure that you can do it. Yeah. And because of that, try to learn them perfectly right now. Then in future, whenever you want to refresh your memory because you did that good, when you start learning, you can just back to the same actually knowledge that you had before very fast because you read them very good at that time. So this is your omega u. Yeah, this is omega u. This is your RU. Yeah, that's a reaction. How can I find this? RU omega u times L divided by 2. Yeah, that's your reaction. Shear diagram for this should be RU go up, the other side will go down, connect them together for uniform load. Yeah. So this side is your RU. We call that VU. Yeah. You can call that VU as well. That's the maximum shear here. But as you might remember, through the shear strength of the beams, I told you that the shear, because it will work with 45 degree, we will go with the maximum about D from face of the support with angle of 45 degree. Yeah. So D from face of the support, we consider that as your maximum shear. So D from face of the support, that's your D. Yeah. From here to here is your D. That's it. How can I calculate this here at here? Yeah, look at this. How can I calculate this one? Sigma Fy equals 0. Okay, sigma Fy means RU upward positive. RU, then omega U, you have omega U up to here. And this distance is your D. Yeah, from here to here is your D, distance D. So minus omega U times D downward, minus omega U times D. Then you have shear here. Your shear is this direction. You are looking for this shear, if I called it V. Yeah. Then negative V is equal 0. That's it. Then we go to other side. Your shear should be RU minus omega U times D. RU is your VU here. This is your RU minus omega times D. That's the equation. If you back on the beams, on the shear, you can see, and we wrote about these equations to find that shear D from face of the support. Is that clear now?
Yeah, thank you. I was just confused because I thought D was the cover above the rebar, but it's also
No.
from
D is not
okay.
the cover. No. Just remember, on that side, I showed something like, let me go to that actually case, because I want to make that come clear. It's not this one. Let me show this. Look at this. From here to here is your D. Yeah, this is your D. This part is for this, from center, at least 1 inch, at least 1 we need to the bottom. So plus distance, T is not from top to the bottom. Top to the bottom is your T. From center to the top is your D. Yeah, clear?
And we use that same D for the distance from the
same
face
D,
of
yeah.
the point. Okay.
That's correct. D
Thank
from
you.
face of the support, the same D. Yep. Okay. So actually, look at this. Most of the class, they're asking that many questions, and that's not good. Yeah. I know that I have to spend more time to answer the questions, but it means that you are listening and you have questions. Even if you should know that, doesn't matter. You are a student. Yeah, you can forget. In future, you cannot forget. You can't. For me, I can't forget. In future, you can't. Right now, you are a student. You can forget, and we have to give you information to actually make sure when you are listening, you can understand. And I'd like to see questions. That's good. Okay. So for moment, positive moment means at the center of the slabs. Yeah. We have A direction and B direction. What does it mean? That's in the example, you can see that, but let me go through this. Long span, LB. Yeah, LB. Short span, LA. Because we have one more actually class next week. I'm not going to complete this today because I think I will confuse you. We have a lot of actually tables, 1, 2, 3, 4, 5 tables. So I don't want to confuse you on this one. This is very easy stuff. So I will give you some information this week, and next week I'm going to complete the rest of this. So we have good time for this. Okay. So in this case, one strip, look at this. This is the strip at B direction. It will go to LA, but look at this long span. So I call this B. Yeah, this is for B. A strip for B. Okay. The other one, a strip for A. Look at this. LA is the length. So this direction, a strip is for A. Hopefully this is completely clear now. So when you have two parts, one of them will go for a strip B. Look at this, CB, MUB, CB times omega U, the load, times B square, LB square times omega U, times CB for this one. It will give you us the maximum positive moment for this strip. What's the width of this strip? 1 foot. As I mentioned, omega U should be pound per square feet times 1 foot, pound per foot. That's it. Omega U, pound per foot. Width of each strip, 1 foot. So the moment that we calculate would be for 1 foot of this at the long side, 1 foot of that for the short side. So you need rebar at this direction, rebar at the other direction, because this is two-way moment, two-way slab. The load will be transferred to both sides, not one direction. So you need to install rebar at both directions. How to calculate them? You have two moments, as you can see. Direction B means this side. You need rebar. Those rebar for B, that's a little confusing, but try to understand, please. Look at this. Rebar for B will go this direction. These are the rebar for the B positive. These are the B. Parallel to B. Rebar for the A should be at the opposite direction. Which side should be bigger, A or B? If I see that rebar, one of them is number 4 at 20 inches, one of them is at 10 inches. So which one should go at what side? Shorter length should be stronger because the more load will go to the short side. Yeah, always. So the LB rebar should be stronger than LA rebar. Just remember this. And you can see when you calculate the moment at the A direction are greater than moment at B directions. That's it. These two are equal. Look at this, 0.036, 0.036. Why? Because this is 1, means both sides are equal. That's a square slab. Yeah, LA divided LB equal 1. And because of that, both sides moments are equal. But if I go with 0.8, look at this. It means that a small side is 80% of the long side. So in this case, 56% should be CA and 0.023 should be your CB. You can see most of the load will go to the other side, to a small direction. Yeah, LA, not LB. Please draw something like this for yourself. It's a little confusing. If you show this, you can understand. And even in example, I will make that more clear. Okay, so this is just for the M positive for dead load. This omega U is for the dead load only. For the live load, we have another one for M positive for CA live load, LL, CB live load, L. Yeah, again, the same thing is exactly the same. All these cases are the same. When you go with case two in all tables are the same. Okay, so MUA, that's the equation. MUB, that's the equation. Find the CA and CB for omega UL 1.6 times live load, the other one 1.2 times dead load. Yeah, so you can find MUA positive dead load, MUA positive dead load, add them together, that's your MU positive. That's it. Yeah, you have two tables. Don't forget for M positive. For M negative, no. We have just one table for dead load plus live load. I put all this with the red line, so whenever you are going to use this, you can pay attention to this. Oh, it's dead load plus live load. For M positive, one of them is dead load, other one is for live load. Yeah, that's it. The process is exactly the same. Case 1 all the way to 9, they are the same. Find CA negative, CB negative, all the same. CA negative, CB negative. Yeah. Why there is no coefficient here? Because the negative moment, this is simply supported. So there is no negative moment. Look at this. This side, 4 sides are fixed connection. You have negative moment at the A direction, negative moment at the Y direction. One more time, let me show this here for negative. For the negative, for A direction, this is 1 foot, the strip of 1 foot. Yeah. So that's negative, means moment here. Yeah. This is your negative moment this side. This is the negative moment this side. Positive moment, we did that with the other actually table. That's for A direction. Yeah. So read CA negative, go to this equation, omega U DL dead load plus live load, 1.2 D, 1.6 live load times 1 foot. We know that we are not going to multiply by 1 foot. Just remember, it's pound per foot times LA square. What's LA? Smallest span. Yeah, smallest span square. The other one, L. Because it's simply supported, there is no negative moment here. I mean, you get 0, 0. Over here, negative for A side and negative for B side. This is your B. Yeah, for B, you will get negative moment here, negative moment here, means top rebar. Here, top rebar, top rebar, top rebar. For positive, bottom rebar this direction, bottom rebar this direction. Perfect, that's it. So over here, why we don't have CA negative here? Because look at this, that's the strip of 1 foot at the A direction. And it simply supports. So there is no negative moment here. Yeah, it's simply supported. There is no coefficient. The other side, for this strip at the B direction, you have fixed and fixed. Then you will get this factor for B direction only. So you will get negative moment here, negative moment here, nothing for the A direction. What about this side? Why we have simply support, but we have number both sides? Because you have for this A direction, you will get negative at one direction. Yeah, that's the factor for this negative. Other side, 0, no moment. For B direction, no negative moment. Yeah. So this factor will go to the negative side only. This factor, negative side A, negative side B, 0, 0. Over here at A direction, you have negative, negative. B direction, 0, nothing. I hope I made that completely clear. As you can see, it's not that hard. At first, you have to do some practice and play with this and see how to read this. As soon as you can read this, that's it. Find the factors, go to this equation, find the moment. Those are for 1 foot. Go to that long equation that I gave you for finding AS. Find AS, find rho, compare with rho mean. That's it. Is that clear? Or any question?
So the decimals in the table, are those for the CA and CB or? Okay, wait.
Look at this. In front of this CA, all these are CA. All these are CB.
And then length A and length B is this length of the slab.
Yeah, you
correct?
know LA square. LA means a small span. Then you will get moment at A direction. Negative means at the supports. Yeah, M negative means at supports. That's it.
Okay, thank you.
Okay. Any other question? Okay. This is the final actually is for calculate the two-way slab. How to calculate the load that is going to the A direction or B direction. Use this equation. This is for dead load and live load again. So find LA, LB times omega U times that omega A, omega B. Look at this. That's it. Means LA, LB, omega U total load. Percentage to the each direction. If it is simply supported, look at this, 50-50, 50% A direction, 50% B direction. Then this actually load that you are calculating will go to the both sides. The problem on this one that you must pay attention is this. Assume that this is your slab at 4 sides. Then for total load for A direction, look at this. This is your, that's important. Pay attention because it's a little maybe confusing. This is your strip at A direction. Right now I'm going at the A direction. Total should be, I will go with this, yeah, with this one. Fixed support, as you can see, fixed support and simple support are the same. Yeah, because total load half will go this way, half that way if it's a square. Okay. So 50% of the load means 0.5. Yeah, omega A. Omega A. That's omega. Times LA. Times LA. Yeah. Times LB. Times omega U is total load that will go to the A side. Yeah. 0.5. LA, LB, omega U. Doesn't mean that one side will go to this side plus this side. Yeah, A direction has 2 supports. So this load is for 2 sides. If I want to find the shear for 1 foot of this, what can I do? I should go with 0.5. Yeah, 0.5. LA, LB, times omega U. First of all, divided by 2. Yeah, because that's the total load going to the A direction. Remember, if I go with this one, this case, 55% for this direction, 45% for the other side. If I go with this, say 60% this side, 40% other side, and because of that, for two-way, as you remember, I showed you something like this. That's based on the work energy method in actually advanced concrete. I will teach to you guys how to find this actually yield point in the one-way or two-way slab. And it means that 66% for if LA over LB is 85 will go to the A direction. A is this direction. 66%, you can see trapezoid to this side and this side, triangular to other side. It's very matched with this. 71, 29. 81, 19, 85, 15. So if it's getting close to the one-way slab, so you will get almost nothing, a small, very small triangle here, a small triangle, big trapezoid, equal almost the uniform load of rectangular on one direction only. So you can see those numbers. Try to see these numbers. What does it mean? So 50% of this will go to either side divided by 2 of total. Whatever it is, 0.71 times LA, LB, omega U, yeah, divided by 2. So I work on this case right now, but if you go with this, instead of that, you will get 81% at the A direction. So 0.81 LA, LB, omega U divided by 2. That's here. So that's the total load for this length. What's this length? LB. So if I want to find the shear for 1 foot of this, what should I do? Divided by LB. That's it. So this one will give us VU for 1 foot. So then what should I do? Minus omega U times D divided by 12. D from face of the support. Yeah, that's your maximum shear in two-way slab. Yeah, as you can see, it's not that hard. And what direction is critical? For sure, A direction. 81% goes to this side. So I don't need to check that side. But if this side is critical, then I will check the other side as well. Maybe that side is critical as well. Is that clear? But if I go with the maximum, and the maximum is not critical, is less than VC times phi. Yeah, phi C, you saw in that equation on that example. I can calculate based on pure concrete. Shear strength based on the pure concrete. Yeah, 2 lambda square root F prime C B times D. Yeah, so you can calculate VC times phi to compare that with your maximum VU. If it's greater than this, that's it. If it's more than that, your shear is more than that, you have to go with the shear reinforcement in a slab. It's very hard and it's not actually something that is usual, it's unusual. So in that case, it's better to go with the thicker slab, make this a little thick. So the weight will go high, but it can help you for shear as well. But as I mentioned, for regular slabs, shear is not critical. Okay, any question on this one?
So I actually had a quick question. Those main coefficients in the first column, where it says 1.0, 0.95, where are those coming from, or what are those like for?
So please let me know which one are you talking about.
Yeah, like where it says 1.0 and then the WA, WB, then 0.95.
So look at this, that's LA divided by LB.
Oh,
Yeah,
okay.
that's it.
Okay.
So you have a slab, one side is 10 feet, another side is 8 feet. 8 divided by 10, you will go to one of these. If you are not in this case, you have to actually interpolate between the nearest of those two.
Okay, so those, it's going to be exactly those numbers. It's not.
Yeah, sometimes if you're fortunate, yes, is exactly. But if it's not, you can see which one is more critical. If it's closer to one side, or just you are going to do a quick review, go with the one that is more critical. But otherwise, interpolate between those two.
Okay, thank you.
Okay, clear? So I hope you like it. This system is very nice, actually, very good, well prepared. And as I mentioned, when I was a BS student, I loved this stuff. And I went and tried to do some actually research to see if it's acceptable, these numbers or not. Then I went and I find some table like this one from Germany. And I like those actually code from Germany as well. Perfect books, very nice, small, and I love those. So I find something like this. similar and actually with more information, but unfortunately with not English language, with German. But in the math, we have numbers, and all around the world the numbers are the same, so it's very easy to understand. So I went through those and compared with those, very close. You could see some difference between those, and they plotted a lot of charts for negative moment, positive moment at both directions, a lot of informations. Yeah, but here we don't have anything. Yeah, for us, because we are changing a lot. In Europe, they have one code. After 30 years, still they have that same code. But in United States, because we have more money and we are spending a lot of tests, so we are changing our code a lot. Yeah, and because of that, sometimes you cannot see that much information about those, because every few years we are changing those. But in Europe countries, they don't have that much money, so they spend one time and they will keep it for, I don't know, 50 years, 60 years. I checked with those, they were very good. And then I made a finite element modeling for this, and I compared with this. And then I put those in one of my books. Unfortunately, the books, these tables are from my book, but the book are not in English, and I couldn't actually put all those information in here. Just I'm giving you those informations, and I have to translate that. But on that book, I compared element analysis, and the results came out very good. Yeah, so because of that, I love these tables, and I have a reason why I love this. And I compared with Germany and that book, and I checked that with ACI and finite element, and the results were acceptable. Okay, any question on this one? If not, the last part is example, but I prefer to actually work on this example next week. Yeah, right now I want to keep you just that you got right now for slab design, and please try to review this tonight. Please do it tonight. Yeah, and try to find my numbers. Check those numbers and find them. Then you can see if you have more questions or not. And then next week, I will answer to your question, and I will review this example, and it should be last part of this class. And that's it. If you have any question, please ask your question. Okay, if you don't have any question, thank you for actually being in the class. For those that they have lab, please stay. After I actually put your name, I put mark in front of your name in my actually chart. Then I will go after the last part of lab for this semester. And tomorrow I will go for the second class. And next week, actually, we don't have anything for the lab, just for asking your questions. And I will be available for those. Okay.
Thank you, Professor.
Thank you.